Representing our real numbers. As I mentioned when we looked at our family of real numbers can be placed on the number line. And there's different ways we can describe them. We could talk about real numbers geometrically. So we use a picture, that's the number line. Algebraically, might be via an equation or an inequation. Interval notation is a way of representing real numbers. Often use that when we're talking about domain and range of functions. Set notation is yet another way. And that's a more formal way of describing numbers. Types of intervals then. What sort of intervals can we have? We can have bounded intervals. And bounded basically has two endpoints, two boundaries if you like. Unbounded, it only has one endpoint and then it might go off to infinity in the other direction. There's no boundary stopping it going anywhere. Closed is if those endpoints are included. So it's like, remember when you're drawing number plane graphs and we say, oh, you dot the boundary or you make the boundary solid. It's the same sort of idea. When you made it solid, it meant it was included. When you made it dotted, it meant the boundary wasn't included. So it's the same here. It's closed or solid, that means the endpoints are included. It's open if the endpoint's not included. It's the actual boundaries not included itself. And then we have this special one, a degenerate. That's just a single point. Just a single point. So if I had x is greater than 5, visually, geometrically, it would look something like that. That is an open, unbounded interval. Goes off to infinity in one direction, and the endpoint, the boundary, is not included. In interval notation, we would write it like that. It looks like I'm writing coordinates down, but it's not. So the parentheses indicate that the boundary is not included. So we use parentheses to indicate that. And then obviously the left-hand number is the left-hand side of the interval and the right-hand one is the right-hand side. This one's going off to infinity. Formally in set notation, I could do something like this. Now in set notation, sets we indicate inside braces. And this is just meaning x. The colon we often use to just mean such that. So x such that x is always bigger than 5. That's all that's really saying. X is less than or equal to 6. Well, that's a closed unbounded. Now the boundary is included. So it's closed unbounded interval. When it is closed, then the endpoint, we don't put a parenthesis, we put a bracket. So the bracket indicates the endpoint is included. X goes between two numbers. So something like that. That one is open, but it's bounded. Has definite endpoints on both sides. So it's open, bounded interval. It looks like I'm saying the coordinates 4, 6, but no, this is interval notation. Then one like this, that would be a closed bounded interval. Well, what about if one endpoint's included and the other one's not? Now it's definitely bounded, but is it open or closed? Ta-da. So we just say bounded. One side's open, one side's closed. So we just say, look, that's a bounded interval. Okay, rational numbers then. They are the ones that can be written as fractions. Okay? Where a and b are integers, of course. I mean, roots 3 on 2 is still a fraction, but it's certainly not a rational number. So we're talking about where a and b are integers. Irrational numbers, they're all the other ones. So numbers that are not rational. And all of these ones can be expressed as unique, infinite decimals. They will go on forever and ever and ever and ever and never stop, like pi. And they're unique. We're going to prove that the square root of 2 is indeed an irrational number. How do we do this? We're going to use a technique called proof by contradiction. Now, you're used to doing what we say is a direct proof. So with your geometry and things like that, that's what we have, a direct proof. Proof by contradiction is an indirect proof. Because what we do is we actually assume the negation of what we're trying to prove. So if it's not irrational, then it must be rational. So I'm going to assume it's actually rational. And I'm going to try and come up with a contradiction. Because if I end up contradicting myself, then my assumption must have been incorrect. That means I can write the square root of 2 as a over b, where a and b are integers. And basically I'm saying it's going to be simplified. So it has no common factors. We've simplified it as far as it can go. There is a neater way of writing that, much shorter. So another way of saying that, you could say where a and b are co-prime. Co-prime. Now co-prime Co-prime does not mean the numbers are prime numbers. Co-prime are simply numbers that don't have a common factor. So co-prime is like a set of numbers, and in that set there is no common factor amongst all of those numbers. So 14 and 15 are co-prime. Now neither of them are actually prime numbers, but together as a set we call them co-prime. In fact, this set, because you've got 2, 4 and 25, as a set they're co-prime. Yes, 2 and 4 share a common factor, but all 3 of them do not share a common factor. So that's what we call co-prime, when the whole set does not share a common factor, other than of course the number 1, because 1's a factor of everything. Okay, back to our proof. If the square root of 2 is a on b, then I can play around with that and say, well, b times the square root of 2 must be equal to a. Reasonable? Square both sides. 2b squared must be equal to a squared. Okay, but hang on a sec. Remember, we said a and b were integers. So 2b squared must be divisible by 2, because we just said it's got a factor of 2. It's 2 times b squared. In other words, a squared is divisible by 2. We know a squared is divisible by 2. But here's the thing. Prime factors of squares must appear in pairs, because if you're doing your factorization, you're always going to get a pair of numbers in a square. 4 is 2 times 2. 9 is 3 times 3. You always get a pair. So any square that's divisible by 2 must also be divisible by 4, because that prime factor of 2 must appear twice. We end up with 4. Thus, I now know a squared is divisible by 4. But if a squared is divisible by 4, it then means it's possible to write 2b squared as 4 times k, where k is some integer. Now, if I divide both sides by 2, I get that b squared is equal to 2k. So a squared and b squared are both divisible by 2. Well, that means they've got a common factor. They're both divisible by 2. And any prime factor of a square has to be a factor of the square root. So that now means a and b have common factors, but my assumption was they had no common factors. That's what we put in that. We said, look, they've got no common factors. There's my contradiction. I've contradicted myself. I started off by saying they have no common factors, and yet I've come down to the conclusion that they do have common factors. Both of those things can't be true. Contradiction. So therefore, what I assumed must be garbage. So square root of 2 is irrational, and we tend to say, look, this is why I can say, by contradiction. I've created a contradiction. So that's the idea of proof by contradiction. Just very quickly, a recap on significant figures and things like that, just to make sure we're on top of it. You see, why is it important? Because our irrational numbers, we can't work them out exactly, then often we'll use an approximation. Certainly happens in science. They're paranoid about exact numbers. They don't like them. They always have to approximate things in science. Mathematicians, we don't mind. We love exact numbers. But when approximating a number, we usually either do it to so many decimal places, that happens a lot, certainly in science, to significant figures. If you're talking about a very, very small number or a really huge number, it's often more practical to write it in scientific notation or something like that. So you end up using significant figures. So how do we actually round off to significant figures? There often is a little bit of confusion sometimes. And if you know how to round off to decimal places, then really it is no difference, other than we start at the first non-zero digit rather than the decimal point. So you start at the first non-zero digit and count the required number, and then do your rounding. So for instance, if I wanted to round this decimal here, 0.050703 to 2 significant figures, I would start at the first non-zero digit, which is 5, and then 1, 2, round off like normal, 0.051. If I wanted to do it to 3, then 507. If I wanted to do it to 4, and that's the interesting one. Unlike rounding the decimal places, in significant figures, if that last number there behind the decimal place is a 0, we write it down. Because the fact of writing it down is telling us it's significant. It just might have been, I pulled out a ruler and it landed exactly on that measurement. So it ended up being 0. There is significance there. Whole numbers becomes fun. I want to round off 3,000 to 2 significant figures. That'll be 3,000. Now let's do it to 3 significant figures. Okay, that's 3,000. And what the heck, let's do it to 4 significant figures. Yeah, that's 3,000. Because now these numbers are not significant, they're there to hold place value. Right? Look at the first one, which I did the 2 significant figures. If I wasn't to write down those last 2 zeros, I'd have the number 30. I've now changed the size of the number. They're not significant, but they're certainly very important. They need to be there. And so we get this ambiguity with whole numbers. But that's why we use scientific notation if it becomes important, because in scientific notation we won't have an issue. That first one becomes 3.0 times 10 to the 3, the next one becomes 3.00 times 10 to the 3, whereas the last one's 3.000 times 10 to the 3. So if we want to avoid ambiguity, we tend to use scientific or standard notation. Let's go back the other way. How do we work out how many significant figures are in a number? Okay, again, start at the first non-zero and just count. How many digits did you just give me? 0.050703. How many significant figures? I start at 5. And so I've got 5 numbers there. There's 5 significant figures. This one here, 1, 2, 3, 4, also has 5. This one here, 1, 2, 3, 4, 5. That one has 6. Again, that 0 at the end, if I was to get rid of it, it doesn't change the value of the number. So it's there for a reason. It must be significant. Otherwise, why did they put it there? Just count to the end of the number. Okay, whole numbers. Here we go. Start at the first number. Go, oh, okay. Well, again, you could say it's got 2, you could say it's got 3, or you could say it's got 4. Right? Because these zeros, are they just there to hold place value, or are they actually significant? Without them giving me more information, I don't know. What I always do, if it's ambiguous, I'm going to always give the biggest answer. I might not be right, but I can't be wrong, unless they give me more information. So I'm saying 4 significant figures for that one. All right, that will do us for today.